right, this is CS50, and this is the start of week 6. So a couple of new tools are now available for you to take advantage of, the first of which is called CS50 Style. So odds are, if you're like me or any of the teaching fellows, you've probably seen a program whose style looks a little something like this. Maybe you start cutting some corners late at night, or you'll deal with it later, and then a TF or CA comes over during office hours, then it's hard for us to read. Well, this code is syntactically correct, and it will compile, and it will actually run, but it's definitely not a 5 for style. But now, if we go into this directory here, and notice that I have conditions2.c, and I run this new command, style50, on this file, conditions2.c, enter, notice that it's informed me that it has been stylized. gedit noticed that the file has been changed on disk. And if I click reload, all your problems are now automated. So that's one of the things we did this weekend. Realize that it is imperfect, because there is some code that it simply won't be able to stylize perfectly. But realize this is now a tool you can take advantage of, if only to sort of tidy up some of the more errantly placed curly braces and the like. But more compellingly now is CS50 check. So with CS50 check, can you actually perform the same correctness tests on your own code that the teaching fellows are able to? This is a command line utility that comes now in the appliance as soon as you do an update 50 as per PSETS4 specifications. And you use it essentially like this. You run the command check 50, then you pass in a command line argument, or more generally known as a switch or a flag. Generally, things that have hyphens are called a switch to a command line program. So -c specifies the checks that you want to run. The tests that you want to run are identified uniquely by this string, 2012/pset4/resize. In other words, that's just an arbitrary but unique string that we use to uniquely identify pset4's correctness tests. And then you specify a space-separated list of the files that you want to upload to CS50 check for analysis. So for instance, if I go into my solution here for resize.c, let me open up a bigger terminal window, and I go ahead and run, let's say, check 50-c 2012/pset4/resize, and then I go ahead and specify the names of the files, so resize.c, and then hit enter. It compresses, it uploads, it checks, and I just failed a whole bunch of tests. So the one in red at top left says that resize and .c and BMP exist. So that was the test. That was the question we asked, and it's red, and it's unhappy because the answer was false. So the white text below, it says expected BMP.h to exist, and that's simply my fault. I forgot to upload it. So I need to upload both files, resize.c and BMP.h. But now notice all of the other tests are in yellow because they haven't run. And so the smiley face is sort of vertical because he's neither happy nor sad, but we have to redress that issue in red before those other checks will run. So let me fix this. Let me zoom out and rerun this time with bmp.h also on the command line, enter. And now, if all goes well, it's going to check and then return a result of, hold your breath, all green, which means I'm doing really well on pset4 so far. So you can see and infer from the descriptive text here exactly what it is we tested. We tested first, do the files exist? We then tested, does resize.c compile? Then we tested, does it not resize a 1 by 1 pixel BMP when n, the resize factor, is 1. Now, if you have no idea what n is, you soon will once you dive into pset4. But that's simply a sanity check to make sure that you're not resizing an image at all if the resize factor is 1. If, by contrast, it resizes a 1 by 1 pixel to a 1 by 1 pixel BMP to 2 by 2 correctly when n is 2, then similarly am I formed accordingly. So in short, this is meant to, one, take the sort of crossing of fingers out of the equation right before you submit your PSET. You will know exactly what your TF will soon know when you go about submitting some of these problem sets. And also, the pedagogical motivation is really to put the opportunity in front of you so that when you know a priori that there's bugs in your code and tests that aren't being passed, you can put in more effective time up front to solve those problems rather than lose points, get feedback from your TF, and then sort of go, like I should have figured that out. Now at least there's a tool to help you find that. It's not going to point out where the bug is, but it will tell you what is symptomatic of it. Now realize the tests aren't necessarily exhaustive. Just because you get a screen full of green smiley faces doesn't mean your code is perfect, but it does mean that it has passed certain tests prescribed by the spec. Sometimes we won't release checks. For instance, whodunit, one of the aspects of pset4, is kind of disappointing if you run the, we sort of give you the answer as to what it is, and there's a number of ways to reveal who the person is in that red noise. So the spec will always specify in the future, for pset5 onward, what checks exist for you. Now you'll notice there's this white URL at the bottom. For now, this is just diagnostic output. If you visit that URL, you'll get a whole bunch of crazy cryptic messages that you're welcome to look through, but it's mostly for the staff so that we can diagnose and debug bugs in check50 itself. So without further ado, let's move on to where we left off. So CS50 library, we took for granted for some weeks, but then last week we started peeling back one of the layers of it. We started putting aside string in favor of what instead? So char star, which has been a char star all this time, but now we don't sort of have to pretend that it's an actual data type string. Rather, it's just been a synonym of sorts for char star. And a string sort of is just this sequence of characters. So why does it make sense to represent strings as char stars? What does a char star represent in the context of this concept of a string? Yeah. Good, the first character, but not quite the first character. It's the address of the first character. So all that's necessary to represent a string in a computer's memory is just the unique address of its very first byte. You don't even have to know how long it is, because how can you figure that out dynamically? Well, you can call string length, excellent. But how does string length work? What does it do? Yeah.
Keep going until you get the null character?
Yeah, exactly. It just iterates with a for loop, while loop, whatever, from start to the end. And the end is represented by \0, the so-called null character. NUL, not to be confused with NULL, which is a pointer, which will come up in conversation again today. So we peeled back a layer of getInt, and then we took a look at getString, and recall that both of those functions, or really getString, was using a certain function to actually parse, that is, read or analyze the user's input. And what was that new function? Scanf, or scanf. It actually comes in a few different flavors. There's scanf, there's scanf, there's fscanf. For now, though, let's focus on the one most easily illustrated. And let me go ahead and open up in the appliance a file like this, scanf1.c. So this is a super simple program, but that does something that we've never done without the help of the CS50 library. This gets an int from a user. So how does this work? Well, on line 16 there, notice that we declare an int called x. And at this point in the story, what is the value of x? Right, who knows? Some garbage value, potentially. So in 17, we just tell the user, give me a number, please. And step 18 is where it gets interesting. So scanf seems to borrow an idea from printf in that it uses these format codes and quotes. %d is, of course, a decimal number. But why am I passing in &x instead of just x? The former is correct. Yeah? Exactly. If the goal of this program, like the function getString itself, getInt itself, is to get an int from the user, I can pass functions all the variables I want. But if I don't pass them by reference or by address or by pointer, all synonymous for today's purposes, then that function has no ability to change the contents of that variable. So this would pass in a copy, just like the buggy version of swap that we've talked about a few times now. But instead, by doing &x, I'm literally passing in what? The address of x. It's like drawing a map for the function called scanf and saying, here, these are directions to a chunk of memory in the computer that you can go store some integer in. So in order for scanf to now do that, what operator, what piece of syntax is it going to have to use, even though we can't see it because someone else wrote this function? What's that? So there's going to be some reading, but only with regard to x here. If scanf is being passed the address of x, syntactically, what operator is bound to exist somewhere inside of scanf's implementation so that scanf can actually write a number to that address? Yeah, so the star. Recall that the star is our dereference operator, which essentially just means go there. So once you've been handed an address, as is the case here, scanf is probably, if we actually looked around at source code, is doing star x, or the equivalent, to actually go to that address and put some value there. Now, as for how scanf gets input from the keyboard, we'll wave our hands out for today. Just assume that the operating system allows scanf to talk to the user's keyboard. But at this point now in line 19, when we simply print out x, it seems to be the case that scanf has put an int in x. So that's exactly how scanf works. And recall last week, that's exactly how getString and getInt and its other family of functions ultimately works, albeit with slight variants like scanf, which just means scan a string instead of the keyboard. But let's take a look at a little variant of this. In scanf2, I actually screwed up. What is wrong, and I'll hide the comment that explains as much, what is wrong with this program, version 2? Be as technical as possible this time. Looks pretty good. It's nicely indented. But, yeah, so, OK, how about let's prune it down to shorter questions. Line 16. What's line 16 doing in precise but technical English? Getting a little awkward. Yes, Michael.
It's pointing to the first letter of a string.
OK, close. Let me tweak that a little bit. Pointing to the first letter of a string, you are declaring a variable called buffer that will point to the first address of a string, or rather that will point more specifically to a char. So notice it's not actually pointing anywhere because there's no assignment operator. There's no equal sign. So all we're doing is allocating the variable called buffer. It happens to be 32 bits because it's a pointer. And the contents of buffer presumably eventually will contain an address of a char. But for now, what does buffer contain? Just some bogus, who knows, some garbage value, because we haven't explicitly initialized it, so we shouldn't assume anything. OK, so now line 17's, OK, what does line 17 do? Maybe that'll warm this up. It prints a string, right? So it prints string please. OK, line 18 is kind of familiar now in that we just saw a variant of this, but with a different format code. So in line 18, we're telling scanf, here is the address of a chunk of memory. I want you to ring in a string, as implied by %s. But the problem is that we have not done a couple of things here. What's one of the problems?
It's trying to dereference a null pointer.
OK, good. Null or just otherwise unknown pointer. So you're handing scanf an address, but you just said a moment ago that that address is some garbage value because we didn't actually assign it to anything. And so you're telling scanf effectively, go put a string here, but we don't know where here yet is. So we haven't actually allocated memory for buffer. Moreover, what are you also not even telling scanf? Suppose this was a chunk of memory, and it wasn't a garbage value, but you're still not telling scanf something important. Yeah.
Where it actually is, the ampersand buffer?
So where it is, so in this case, it's OK. Because buffer is already declared as a pointer with the star piece of syntax, we don't need to use ampersand because it's already an address. But I think I heard it here. Good. We're not telling scanf how big this buffer is, which means even if buffer were a legit pointer, we're saying scanf, put a string here. But here could be 2 bytes, it could be 10 bytes, it could be a megabyte. Scanf has no idea. And because this is just a chunk of memory, presumably, it's not a string yet. It's only a string once you write characters and a \0 to that chunk of memory. Now, it's just some chunk of memory. Scanf won't know when to stop writing to that address. So if you recall some examples in the past where I just sort of randomly typed on the keyboard trying to overflow a buffer, and we talked on Friday about exactly that. If an adversary somehow injects into your program a much bigger word or sentence or phrase than you were expecting, you can overrun a chunk of memory, which can have bad consequences, like taking over the whole program itself. So we need to fix this somehow. So let me zoom out and go into version 3 of this program that's a little bit better. So in this version, notice the difference. In line 16, I'm again declaring a variable called buffer, but what is it now? It's an array of 16 chars. So this is good, because this means I can now tell scanf, here is an actual chunk of memory. You can almost think of arrays as being pointers now, even though they're not actually equivalent. They can have they'll behave differently in different contexts. But it's certainly the case that buffer is referencing 16 contiguous chars, because that's what an array is and has been for some weeks now. So here I am telling here I am telling scanf, here's a chunk of memory. This time it's actually a chunk of memory, but why is this program still exploitable? What's wrong still? I've said give me 16 bytes, but exactly. What if the user types in 17 characters or 1,700 characters? In fact, let's see if we can't trip over this mistake now. So it's better, but not perfect. Let me go ahead and make scanf3 to compile this program. Let me run scanf3, string please, hello, and we seem to be OK. Let me try a slightly longer one, hello there. OK, let's do hello there, how are you today? Enter. Getting kind of lucky here. Let's see. Hello there. How are you? All right. Damn it. OK. So we got lucky. Well, let's see if we can't fix this. All right. No, it's not going to let me copy. Let's try this again. All right. Stand by. So see how long I can pretend to focus while still doing this. Damn it. That's rather appropriate, actually. OK. There we go. Whew. OK. Point made. OK. So this, embarrassing though it also is also one of the sources of great confusion when writing programs that have bugs, because they manifest themselves only once in a while sometimes. The reality is that even if your code is completely broken, it might only be completely broken once in a while, because sometimes essentially what happens is the operating system allocates a little more memory than you actually need for whatever reason, and so no one else is using the memory right after your chunk of 16 characters. So if you go to 17, 18, 19, whatever, it's not such a big deal. Now, the computer, even if it doesn't crash at that point, might eventually use byte number 17 or 18 or 19 for something else, at which point your data that you put there, albeit excessively long, is going to get overwritten potentially by some other function. So it's not necessarily going to remain intact, but it won't necessarily cause a seg fault. But in this case, I finally provided enough characters that I essentially exceeded my segment of memory, and bam, the operating system said, sorry, that's no good, segmentation fault. And let's see now if what remains here in my directory. Notice that I have this file here, core. Notice that this is, again, called a core dump. It's essentially a file that contains the contents of your program's memory at the point at which it crashed. And just to try a little example here, let me go in here and run gdb on scanf3, and then specify a third argument called core. And notice here that if I list the code, we'll be able, as usual with gdb, start walking through this program. And I can run it, and as soon as I hit, as with the step command in gdb, as soon as I hit the potentially buggy line after typing in a huge string, I'll be able to actually identify it here. So more on this, though, in section in terms of core dumps and the like, so that you can actually poke around inside of the core dump and see on what line the program failed you. So any questions then on pointers and on addresses? Because today onward, we're going to start taking for granted that these things exist, and we know exactly what they are. Now, yes? Good question. How come I didn't have to put an ampersand next to the character array, as I did previously with most of our examples? So arrays, the short answer is arrays are a little special. You can almost think of buffer as actually being an address. And it just so happens to be the case that the square bracket notation is a convenience, so that we can go into bracket 0, bracket 1, bracket 2 without having to use the star notation. Now, that's a bit of a white lie, because arrays and pointers are, in fact, a little bit different, but they can often, but not always, be used interchangeably. So in short, when a function is expecting a pointer to a chunk of memory, you can either pass it an address that was returned by malloc, and we'll see malloc again before long, or you can pass it the name of an array. You don't have to do ampersand with arrays, because they are already essentially like addresses. That's the one exception. The square brackets make them special. Could you put an ampersand next to the buffer? Not in this case. So that would not work because of, again, this corner case where arrays aren't quite actually addresses. But we'll perhaps come back to that before long with other examples. All right, so let's try to solve a problem here. So we have a data structure that we've been using for some time known as an array. Case in point, that's what we just had. But arrays have some upsides and downsides. So arrays are nice. Why? What's one thing that you like, to the extent you like arrays, about arrays? What's convenient about them? What's compelling? Why did we introduce them in the first place? Yeah? Good. So with an array, you can store a lot of data, and you don't have to necessarily use all of it. So you can over-allocate, which might be convenient. If you don't know in advance how many of something to expect, getString is a perfect example. GetString, written by us, has no idea how many chars to expect. So the fact that we can allocate chunks of contiguous memory is good. Arrays also solve a problem we saw a couple weeks ago now, where your code starts to devolve into something very poorly designed. Recall that I created a student structure called David, and then that was actually an alternative, though, to having a variable called name, and another variable called, I think, house, and another variable called ID. Because in that story, I then wanted to introduce something else, like Rob, into the program. So then I decided, wait a minute, I need to rename these variables. Let's call mine name1, ID1, house1. Let's call Rob's name2, house2, ID2. But then wait a minute, what about Tommy? So then we had 3 more variables. We introduced someone else, 4 sets of variables. So the world started to get messy very quickly. So we introduced structs. And what's compelling about a struct? What does a C struct let you do? It's really awkward today. Yeah, it's a what? Yeah, it allows, so specifically typedef allows you to create a new data type, and struct, the struct keyword, allows you to encapsulate conceptually related pieces of data together and thereafter call them something like a student. So that was good, because now we can model much more sort of conceptually consistent the notion of a student in a variable, rather than arbitrarily having one for a string, one for an ID, and so forth. So arrays are nice because they allow us to start cleaning up our code. But what is a downside now of an array? What can you not do? Yeah? You have to know how big it is. So it's kind of a pain. Those of you with prior programming experience know that in a lot of languages like Java, you can just ask a chunk of memory, specifically an array, how big are you, with a length property, so to speak. And that's really convenient. In C, you can't even call strlang on a generic array, because strlang, as the word implies, is only for strings. And you can figure out the length of a string because of this human convention of having a \0. But an array, more generically, is just a chunk of memory. If it's an array of ints, there's not going to be some special character at the end waiting for you. You have to remember the length of an array. Another downside of an array reared its head in getString itself. What's another downside of an array? Sure, just you and me today. It's what? It's declared on the stack. OK, so declared on the stack. Why don't you like that? Gets reused. OK, so if you use an array to allocate memory, you can't, for instance, return it because it's on the stack. So OK, so that's a disadvantage. And how about one other with an array? Once you allocate it, you're kind of screwed if you need more space than that array has. So then we introduced recall malloc, which gave us the ability to dynamically allocate memory. But what if we tried a different world altogether? What if we wanted to solve a couple of those problems? So we instead, iPad has fallen asleep here. What if we instead wanted to essentially create a world that's no longer like this? So this is an array. And of course, this kind of deteriorates once we hit the end of the array. And I now no longer have space for another integer or another character. So what if we sort of preemptively say, well, why don't we relax this requirement that all these chunks of memory be contiguous, back to back? And why don't, when I need an int or a char, just give me space for one of them. And when I need another, give me another space. And when I need another, give me another space. The advantage of which now is that if someone else takes the memory over here, no big deal. I'll just take this additional chunk of memory here, and then this one. Now, the only catch here is that this almost feels like I have a whole bunch of different variables. This feels like 5 different variables potentially. But what if we steal an idea from strings whereby we somehow link these things together conceptually? And what if I did this? So this is my very poorly drawn arrow. But suppose that each of these chunks of memory pointed to the other, and this guy, who has no sibling to his right, has no such arrow. So this is, in fact, what's called a linked list. This is a new data structure that allows us to allocate a chunk of memory, then another, then another, then another, anytime we want during a program. And we remember that they're all somehow related by literally chaining them together. And we did that pictorially here with an arrow. But in code, what would be the mechanism via which you could somehow connect, almost like Scratch, one chunk to another chunk? Yeah, so we could use a pointer, right? Because really, the arrow that's going from the top left square, this guy here, to this one could just contain inside of this square, not just some int, not just some char, but what if I actually allocated a little extra space so that now each of my chunks of memory, even though this is going to cost me, now looks a little more rectangular, where one of the chunks of memory is used for a number, like the number 1. And then if this guy stores the number 2, this other chunk of memory is used for an arrow, or more concretely, a pointer. And suppose I store the number 3 over here, while I use this to point at that guy. And now this guy, let's suppose I only want 3 such chunks of memory. I'll just draw a line through that indicating null. There is no additional character. So indeed, this is how we can go about implementing something that's called a linked list. So a linked list is a new data structure, and it's a stepping stone toward much fancier data structures that begin to solve problems along the lines of Facebook-type problems and Google-type problems, where you have huge data sets, and it no longer cuts it to just store everything contiguously and use something like linear search or even something like binary search. You want even better running times. In fact, one of the holy grails we'll talk about later this week or next is an algorithm whose running time is constant. In other words, it always takes the same amount of time, no matter how big the input is. And that would indeed be compelling, even more so than something logarithmic. So what is this on the screen here? So each of the rectangles is exactly what I just drew by hand. But the thing all the way on the left is a special variable. It's going to be a single pointer, because the one gotcha with a linked list, as these things are called, is that you have to hang on to one end of the linked list. Just like with a string, you have to know the address of the first char. Same deal for linked lists. You have to know the address of the first chunk of memory, because from there you can reach every other one. So downside, what price are we paying for this versatility now of having a dynamically sizable data structure that if we ever need more memory, fine, just allocate one more chunk and draw a pointer from the old to the new tail of the list? Yeah. Takes twice as much space. So that's definitely a downside. And we've seen this trade-off before between time and space and flexibility, whereby now we need not 32 bits for each of these numbers. We really need 64, 32 for the number and 32 for the pointer. So, but hey, I like 2 gigabytes of RAM. Adding another 32 bits here and here doesn't seem that big of a deal. But for large data sets, definitely adds up to literally twice as much. What's another downside now? Or what feature do we give up if we represent lists of things with a linked list and not an array?
You can't traverse it backwards.
Can't traverse it backwards. So you're kind of screwed if you're walking from left to right using a for loop or a while loop, and then you realize, ooh, I want to go back to the beginning of the list. You can't, because these pointers only go from left to right, as the arrows indicate. Now, you could remember the start of the list with another variable, but that's a complexity to keep in mind. In array, no matter how far you go, you can always do minus, 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 and go back from whence you came. What's another downside here? Yeah? You could. So you've actually just proposed a data structure called a doubly linked lists. And indeed, you would just add another pointer to each of these rectangles that goes the other direction, upside of which is now you can traverse back and forth, downside of which is now you're using 3 times as much memory as we used to, and also adding complexity in terms of the code you have to write to get it right. But these are all perhaps very reasonable trade-offs if the reversal is more important. Yeah? Ah, good. You can't really have a 2D linked list. So you could. It's not nearly as easy as an array. Like an array, you just do open bracket, close bracket, and you get some two-dimensional structure. You could implement a two-dimensional linked list if you do add, as you proposed, a third pointer to each of these things. And if you think about another list coming at you, 3D style, from the screen to all of us, which is just another link, another chain of some sort. So we could do it, but it's not as simple as just typing open bracket, square bracket. Yeah? Good. So this is a real kicker. These algorithms that we've sort of pined over, like, oh, binary search. You can search an array of numbers on the board or a phone book so much more quickly if you use divide and conquer and a binary search algorithm. But binary search required two assumptions. One, that the data was sorted. Now, we can presumably keep this sorted, so maybe that's not a concern. But binary search also assumed that you had random access to the list of numbers. And an array allows you to have random access. And by random access, I mean if you're given an array, how much time does it take you to get to bracket 0? One operation. You just use square bracket 0 and you're right there. How many steps does it take to get to location 10? One step, right? You just go to bracket 10 and you're there. By contrast, how do you get to the 10th integer in a linked list? You have to start at the beginning because you're only remembering the beginning of a linked list, just like a string is being remembered by the address of its first char. And to find that 10th int or that 10th character in a string, you have to search the whole damn thing. So again, we're not sort of solving all of our problems. We're introducing new ones, but it really depends on what you're trying to design for. So in terms of implementing this, we can borrow an idea from that student structure. The syntax is very similar, except now the idea is a little more abstract than house and name and ID. But I'd propose that we could have a data structure in C that is called node, as the last word on the slide suggests, inside of a node. And a node is just a generic container in computer science. It's usually drawn as a circle or square or rectangle, as we've done. And in this data structure, we have an int n. So that's the number I want to store. But what is this second line? Struct node star next. Why is this correct? Or what role does this thing play? Even though it's a little cryptic at first glance. Yeah? Exactly. So the star sort of spoils that it's a pointer of some sort. The name of this pointer is arbitrarily next, but we could have called it anything we want. But what does this pointer point to? Exactly. It points to another such node. Now, this is sort of a curiosity of C. Recall that C is read by a compiler top to bottom, left to right, which means if this is a little different from what we did with the student. When we define a student, we actually did not put a word there. It just said typedef. Then we had int ID, string name, string house, and then student at the bottom of the struct. This declaration is a little different because, again, the C compiler is a little dumb. It's only going to read top to bottom. So if it reaches the second line here where next is declared, and it sees, ooh, here's a variable called next. It's a pointer to a struct node. The compiler is going to realize, what is a struct node? I've never heard of this thing before, because the word node might not otherwise appear until the bottom. So there is this redundancy. You have to say struct node here, which you can then shorten later on thanks to typedef down here. But this is because we are referencing the structure itself inside of the structure. So that's the one gotcha there. All right, so some interesting problems are going to arise. We've got a list of numbers. How do we insert into it? How do we search it? How do we delete from it? Especially now that we have to manage all of these pointers. You thought pointers were sort of mind-bending when you had one of them just trying to read it into it. Now we have to manipulate an entire list's worth. Why don't we take our 5-minute break here, and then we'll bring some folks up on stage to do exactly that. All right. So C is much more fun when it's acted out. Who would literally like to be first? OK, come on up. You are first. Who would like to be 9? OK, 9. How about 9? 17. Little click here. 22 and 26 in that front row. And then how about someone over there being pointed at? You are 34. OK, 34, come on up. OK, first is over there. OK, all 4 of you guys. And who'd we say for 9? Who is our 9? Who really wants to be 9? All right, come on, be 9. All right, so here we go. 34. We'll meet you over there. All right, so first part is make yourselves look like that. All right, 26, 22, 17. Good. If you can stand off to the side, because we're going to malloc you in a moment. All right. Good? Good? OK, excellent. So let's ask a couple of questions here. And actually, what's your name? Nina? Anita. OK, Anita, come on over here. So Anita is going to help us sort of solve one fairly simple question at first, which is how do you find whether or not a value is in the list? Now, notice that first, represented here by Lucas, is a little different. And so his piece of paper is deliberately sideways, because it's not quite as tall and not quite as doesn't take up as many bits, even though technically it's the same size of paper, just rotated. But he's a little different in that he's only 32 bits for a pointer. And all of these guys are 64 bits, half of which are the number, half of which is a pointer. But the pointer is not depicted. So if you guys could somewhat awkwardly use your left hand to point at the person next to you. And you're number 34. What's your name?
Ari.
Ari, so your left hand, actually hold the paper in your right hand, and left hand goes straight down. You represent null on the left. All right, so now our human picture is very consistent. This is actually how pointers work. All right, so, and if you can scrunch a little bit this way so I'm not in your way. Anita here, find me the number 22, but assume a constraint of not humans holding up pieces of paper, but this is a list, and you only have Lucas to begin with, because he is literally the first pointer. So suppose you yourself are a pointer, and so you too have the ability to point at something. So why don't you start by pointing at exactly what Lucas is pointing at? Good. And let me enact this out over here. Just for the sake of discussion, let me pull up a blank page here. How do you spell your name? OK. Nina. So let's say node star Anita gets Lucas. OK. So, well, we shouldn't call you Lucas. We should call you first. OK. So why is this, in fact, consistent with reality here? So one, first already exists. So first has been allocated, presumably somewhere up here, node star first. And it's been allocated a list somehow. I don't know how that happened. That happened before class started. This linked list of humans has been created. And now at this point in the story, this is all going on Facebook apparently later. So at this point in the story, Anita has been initialized to be equal to first, which doesn't mean that Anita points at Lucas. Rather, she points at what he points at, because the same address that's inside of Lucas's 32 bits, 1, 2, 3, is now also inside of Anita's 32 bits, 1, 2, 3. OK, so now find 22. How would you go about doing this? What's that? Point to whatever. OK, so go ahead and enact it out as best you can here. Good? And good. And now you're pointing at, what's your name with 22? Ramon. So Ramon is holding up 22. You have now done a check. Does Ramon equal 22? And if so, for instance, we can return true. So let me, while these guys stand here somewhat awkwardly, let me do something quickly like bool, let's see, find. I'm going to go ahead and say node star list int n. I'll be right back with you guys. Just have to write some code. And now I'm going to go ahead and do this. Node star Anita gets list. And I'm going to go ahead and say while Anita is not equal to null. OK, the metaphor here is getting a little stretched. But while Anita is not equal to null, what do I want to do? If Anita, I need some way of referencing the integer that Anita's pointing at. So in the past, when we had structures, which a node is, we used the dot notation. And we would say something like Anita.n. But the problem here is that Anita is not a struct per se. What is she? She's a pointer. So really, if we want to use this dot notation, and this is going to look deliberately a little cryptic, we'd have to do something like go to whatever Anita's left hand is pointing at, and then get the field called n. So Anita is a pointer. But what is star Anita? What do you find when you go to what Anita's pointing at? A struct, a node. And a node, recall, has a field called n, because it has, recall, these two fields, next and n, that we saw a moment ago right here. So to actually imitate this in code, we could do this and say if Anita, star Anita.n, with the parentheses, equals n, the n that I'm looking for. Notice that the function was passed in the number I care about. Then I can go ahead and do something like return true. Else, if that's not the case, what do I want to do? How do I translate to code what Anita did so intuitively by walking through the list? What should I do up here to simulate Anita taking that step to the left, that step to the left? What's that? OK, good. Not a bad idea. But in the past when we've done this, we've done like Anita ++, right? Because that would add the number 1 to Anita, which would typically point at the next person, like Ramon, or the person next to him, or the next to him person down the line. But that's not quite good here, because what does this thing look like in memory? OK, not that. We have to disable that. So it looks like this in memory. And even though I've drawn 1 and 2 and 3 close to one another, if we really simulate this, can you guys, while still pointing at the same people, can some of you take a random step back, some of you a random step forward? So this mess is still a linked list, but these guys could be anywhere in memory. So Anita ++ is not going to work. Why? What's at location Anita ++? Like, who knows? It's some garbage value. It's some other value that just so happens to be interposed among all of these nodes just by chance. Because we're not using an array, we allocated each of these nodes individually. OK, if you guys can clean yourselves back up, let me propose that instead of Anita ++, we instead do Anita gets, well, why don't we go to whatever Anita's pointing at and then do .next. So in other words, we go to Ramon, who's holding the number 22, and then .next is as though Anita would be copying his left-hand pointer. But she wouldn't go farther than Ramon because we found 22. But that would be the idea. Now, this is a god-awful mess. Honestly, like, no one will ever remember this syntax. And so thankfully, it's actually a little deliberate. Oh, you didn't actually see what I wrote. This would be more compelling if you could. Voila. So behind the scenes, I was solving this problem this way. So Anita, to take that step to the left, first we do go to the address that Anita's pointing at, and where she will find not only n, which we just checked for comparison's sake, but she will also find next. In this case, Ramon's left hand pointing to the next node in the list. But this is the god-awful mess to which I referred earlier. But it turns out C lets us simplify this. Instead of writing parenthesis, star, Anita, close parenthesis, we can instead just write Anita, arrow, n. And it's the exact same thing functionally, but it's a lot more intuitive, and it's a lot more consistent with the picture that we've been drawing all this time using arrows. So lastly, what do we need to do at the end of this program? There's one line of code remaining. Return what? False, because if we get through the whole while loop and Anita is in fact null, that means she went all the way to the end of the list where she was pointing at, what's her name again? Ari's left hand, which is null. So Anita is now null. And I realize you're just kind of standing here awkwardly in limbo because I'm kind of going off on a monologue here. But we'll involve you again in just a moment. Anita is null at that point in the story, so the while loop terminates, and we have to return false. Because if she got all the way to Ari's null pointer, then there was no number that she sought in the list. So we can clean this up too. But this is a pretty good implementation then of a traversal function, a find function for a linked list. It's still just linear search, but it's not as simple as ++ing a pointer or ++ing an I variable, because now we can't guess where each of these nodes are in memory. We have to literally follow the trail of breadcrumbs, or more specifically pointers, to get from one node to another. Well, now let's try another one. If Anita, you want to come back here, why don't we go ahead and allocate one other person from the audience? Malloc, what's your name? Rebecca. Rebecca has been mallocked from the audience, and she is now storing the number 55. And the goal at hand now is for Anita to insert Rebecca into the linked list here in its appropriate place. So come on over here for just a moment. So I have just done something like this. I have done node star. And what's your name again? Rebecca. OK, Rebecca gets malloc size of node. Just like we have allocated things like students and whatnot in the past, we just need the size of a node. So now Rebecca is pointing at what? So Rebecca has two fields inside of her, one of which is 55. So let's do that. Rebecca, arrow n, gets 55. But then Rebecca, arrow next, should be, like right now, her hand's just kind of, who knows? It's pointing at some garbage value. So why don't, for good measure, we at least do this so that left hand is now at her side. So now, Anita, take it from here. You have Rebecca having been allocated, go ahead and find where we should put Rebecca. Good? Very good. OK, good. And now we need you to provide a bit of direction. So you've reached Ari. His left hand is null, but Rebecca clearly belongs to the right. So how do we have to alter this linked list in order to insert Rebecca into the appropriate place? If you could literally like move people's left hands around as needed, we'll fix the problem that way. OK, good. All right, and meanwhile, Rebecca's left hand is now by her side. All right, so that was too easy. Let's try allocating. We're almost done. 20. OK, come on up. 20 has been allocated. So let me go ahead and say again here, we've just done node star side. We have malloc of size of node. We then do the same exact syntax as we did before for 20. And I'll do next gets null. And now it's up to Anita to insert you into the linked list. If you could play that exact same role. Execute. OK, good. Now think carefully before you start moving left hands around. You by far got the most awkward role today. Whose hand should be moved first? OK, wait, I'm hearing some no's. If some folks would politely like to help solve an awkward situation here. Who instead should Anita, whose left hand should be updated first, perhaps? Yeah. OK, Saad's. Why, though? OK, good. Because if we move, what's your name? Marshall. If we move his hand first down to null, now we have literally orphaned 4 people in this list because he was the only thing pointing at Ramon and everyone to the left. So updating that pointer first was bad. So let's undo that. OK, so good. And now go ahead and move the appropriate left hand, pointing at Ramon. So this feels a little redundant. Now there's 2 people pointing at Ramon, but that's fine because now how else do we update the list? What other hand has to move? Excellent. Now have we lost any memory? OK, no. So good. Let's see if we can't break this once more. Mallocing one last time. Number 5 all the way in back. Come on down. Yes, very exciting. Woo! OK, so what's your name? Ron. OK, so you are mallocked as number 5. So we've just executed code that's almost identical to these with just a different name. OK, excellent. Now, Anita, good luck. Inserting number 5 into the list now. Good. And? Excellent. So this is really the third of 3 total cases. We first had someone at the end, Rebecca. We then had someone in the middle. Now we have someone at the beginning. And in this example, we now had to update Lucas for the first time because the first element in the list now has to point at a new node, who in turn is pointing at node number 9. So this was a hugely awkward demonstration, I'm sure. So a big round of applause for these guys if we could. Nicely done. All right, that's all. You may keep your pieces of paper as a little memory. All right, so it turns out that doing this in code is not quite as simple as just moving hands around and pointing pointers at different things. But realize that when it comes time to implement something like a linked list or a variant of it, if you focus on really these basic fundamentals, the sort of bite-sized problems I have to figure out, is it this hand or this hand, realize that what is otherwise a fairly complex program can in fact be reduced to fairly simple building blocks like this? Well, let's take things in a more sophisticated direction still. So we now have the notion of a linked list. We also have, thanks to the suggestion back there, a doubly linked list, which looks almost the same, but now we have 2 pointers inside of the struct instead of 1. And we could probably call those pointers previous and next, or left or right, but we do in fact need 2 of them. The code would be a little more involved. Anita would have had to do more work here on the stage, but we could certainly implement that kind of structure. In terms of running time, though, what would be the running time for Anita of finding a number n in a linked list now? Still big O of n, so it's no better than linear search. We can't do binary search, though, again. Why was that the case? You can't jump around, right? Even though we could obviously see all the humans on the stage, and Anita could have just eyeballed it and said, here is the middle of the list, she wouldn't know that if she were the computer program, because the only thing she had to latch onto at the start of the scenario was Lucas, who was the first pointer. So she would necessarily have to follow those links, counting her way until she found roughly the middle. And even then, she's not going to know when she's reached the middle unless she goes all the way to the end to figure out how many there are, then backtracks, and that too would be hard unless you had a doubly linked list of some sort. So solving some problems today, but introducing others. Well, what about a different data structure altogether? So this is a photograph of the trays in Mather House. And in this case, we have a data structure we've also kind of already been talking about. We've talked about a stack in the context of memory. And that's sort of deliberately named because a stack in the terms of memory is effectively a data structure that has more and more stuff layered on top of it. But the interesting thing about a stack, as is the case in reality, is that it's a special kind of data structure. It's a data structure whereby the first element in is the last element out. So if you are the first tray to be put onto the stack, you're going to be, unfortunately, the last tray to be taken off the stack. And that's not necessarily a good thing. Conversely, you can think about it as the other way around. The last in is the first out. Now, do any scenarios come to mind where having a stack data structure, where you have that property of the last in, first out, is actually compelling? Is that a good thing? Is that a bad thing? Right? It's definitely a bad thing if these trays weren't all identical and they were all sort of special, different colors or whatnot, and the color you want is all the way at the bottom. Of course, you can't get that without great effort. You have to start from the top and work your way down. What if, similarly, what if you were one of these fanboys who waits up all night trying to get an iPhone and lines up at a place like this, right? So wouldn't it be nice if the Apple Store were a stack data structure? Yay, nay? Right, it's only good for the people who show up at the last possible minute and then get plucked off the queue. And in fact, the fact that I was so inclined to say queue is actually consistent with what we would call this kind of data structure, one in reality where order does matter, and you want the first one in to be the first one out, if only for the sake of human fairness. We'll generally call that a queue data structure. So it turns out, besides linked lists, we can start using these same basic ideas and start creating new and different types of solutions to problems. So for instance, in the case of a stack, we could represent a stack using a data structure like this, I would propose. So in this case, I've declared a struct, and I've said inside of this structure is an array of numbers, and then a variable called size. And I am going to call this thing a stack. Now, why does this actually work? Well, in the case of a stack, I could draw this effectively on the screen as an array. So here is my stack. Those are my numbers. And we'll draw them as this, 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 this. And then I have some other data member here, which is called size. So this is size, and this is numbers. And collectively, the whole iPad here represents one stack structure. Now, by default, size is presumably got to be initialized to 0. And what's inside of the array of numbers initially when I first allocate an array? Garbage. Who knows? And it doesn't actually matter. It doesn't matter if this is like 1, 2, 3, 4, 5, completely randomly, by bad luck, stored in my structure, because so long as I know that the size of this stack is 0, well, then I know programmatically just don't look at any of the elements in the array. It doesn't matter what's there, just don't look at them, as would be the implication of a size of 0. But suppose now I go ahead and insert something into the stack. I want to insert the number 5. So I put number 5 here, and then what do I put down here? Well, now I would actually put down 1 for the size. And now the stack is of size 1. What if I go ahead and insert the number, let's say 7 next? This then gets updated to 2. And then we'll do 9. And then this gets updated to 3. But the interesting feature now of this stack is that I'm supposed to remove which element if I want to pop something off of the stack, so to speak. So 9 would be the first thing to go. So how should the picture change if I want to pop an element off the stack, much like a tray in Mather? Yeah. Exactly. All I do is set size to 2. And what do I do with the array? I don't have to do anything. I could, just to be anal, put a 0 there or a -1 or something to signify that this is not a legit value. But it doesn't matter, because I can just record outside of the array itself how long it is, so that I know only look at the first 2 elements in this array. Now, if I go and add the number 8 to this array, how does the picture change next? Yeah, so this just becomes 8. And this becomes 3. I'm cutting a few corners here. So now we have 5, 7, 8, and we're back to a size of 3. So this is pretty simple to implement. But when are we going to regret this design decision? When do things start to go very, very wrong? Yeah. When you want to go back and get the first element you put in. So it turns out here, even though a stack is an array underneath the hood, these data structures we've started talking about are also generally known as abstract data structures, whereby how they're implemented is completely besides the point. A data structure like a stack is supposed to support operations like push, which pushes a tray onto the stack, and pop, which removes an element from the stack. And that's it. So if you were to download someone else's code who'd already implemented this thing called a stack, that person would have written only 2 functions for you, push and pop, whose sole purpose in life would be to do exactly that. You, or him or her who implemented that program, would have been entirely the one to decide how to implement the semantics of pushing and popping underneath the hood, or the functionality of pushing and popping. And I have made a somewhat short-sighted decision here by implementing my stack with this simple data structure y. When does this data structure break? At what point do I have to return an error when the user calls push, for instance? Exactly. If there's no more space, if I've exceeded capacity, which is all caps because it suggests that it's some kind of global constant, well, then I'm just going to have to say, sorry, I can't push another value onto the stack. Much like in Mather, at some point, they're going to hit the top part of that little cabinet. There's no more space or capacity in the stack, at which point there's some kind of error. They have to put the element somewhere else, the tray somewhere else, or nowhere at all. Now, with a queue, we could implement it a little differently. A queue's a little different in that underneath the hood, it can be implemented as an array, but why in this case am I proposing to also have a head element representing the head of the list, the front of the list, the first person in line at the Apple Store, in addition to size? Why do I need an additional piece of data here? Well, think back to what numbers is. If I've drawn it as follows, suppose this is now a queue instead of a stack. The difference being, just like the Apple Store, a queue is fair. The first person in line at the start of the list, number 5 in this case, he or she is going to be led into the store first. So let's do that. Suppose that this is the state of my queue at this moment in time, and now the Apple Store opens, and the first person, number 5, is led into the store. How do I change the picture now that I have dequeued the first person at the front of the line? What's that? So change the head. So, right, 5 disappears. So in reality, it's as though, how best to do this? So in reality, it's as though this guy kind of disappears. So what would number 7 do in an actual store? They would sort of take a big step forward. But what have we sort of come to appreciate when it comes to arrays and moving things around? Like, that's kind of a waste of your time, right? Why do you have to be so anal as to have the first person at the start of the line at physically the start of the chunk of memory, right? That's completely unnecessary. Why? What could I just remember instead? Exactly. I could just remember with this additional data member, head, that now the head of the list is no longer 0, which it was a moment ago. Now it's actually the number 1. So in this way, I get a slight optimization. Just because I've dequeued someone from line at the start of the line at the Apple Store doesn't mean everyone has to shift, which recall is a linear operation. I can instead spend constant time only and achieve then a much faster response. But the price I'm paying is what? To gain that additional performance and not having to shift everyone. Yeah. Can't add more people. Well, that problem's orthogonal to the fact that we're not shifting people around. Like, it's still an array. So whether or not we shift everyone or not, oh, I see what you mean. OK, so actually, I agree with what you're saying in that it's almost as though we're now never going to use the start of this array anymore. Because if I remove 5, then I remove 7, but I only put people to the right, feels like I'm just wasting space, and eventually my queue disintegrates into nothing at all. So we could just have people wrap around. And we could think of this array really as some kind of circular structure, but we use what operator in C to sort of do that kind of wraparound? The modulo operator. Right? It'd be a little annoying to think through how do you do the wraparound, but we could do it. And we could start putting people at what used to be the front of the line, but we just remember with this head variable who the actual head of the line actually is. So what if instead, what if our goal ultimately, though, was to look up numbers, as we did here on stage with Anita, but we really kind of want the best of all these worlds. We want more sophistication than array allows because we want the ability to dynamically grow the data structure, but we don't want to have to resort to something that was, we pointed out in the first lecture, was not an optimal algorithm, that of linear search. Well, it turns out that you can, in fact, achieve, or at least close to, constant time, whereby someone like Anita, if she configures her data structure not to be a linked list, not to be a stack, not to be a queue, could in fact come up with a data structure that allows her to look up things, even words, not just numbers, in what we'll call constant time. And in fact, looking ahead, one of the P sets in this class is almost always a implementation of a spell checker, whereby we give you, again, some 150,000 English words, and the goal is to load those into memory and rapidly be able to answer questions of the form is this word spelled correctly? And it would really suck if you had to iterate through all 150,000 words to answer that. But in fact, we'll see that we can do it in very, very quick time. And it's going to involve implementing something called a hash table. And even though at first glance this thing called the hash table is going to let us achieve these super rapid response times, it turns out that there is, in fact, a problem. When it comes time to implement this thing called, again, I'm doing it again. I'm the only one here. All right. So when it comes time to implementing this thing called a hash table, we're going to have to make a decision. How big should this thing actually be? And when we start inserting numbers into this hash table, how are we going to store them in such a way that we can get them back out as quickly as we got them in? But we'll see before long that this question of when everyone's birthday is in the class will be quite germane. It turns out that, in this room we've got a few hundred people, so the odds that 2 of us have the same birthday is probably pretty high. Right? What if there were only 40 of us in this room? What are the odds of someone having 2 people having the same birthday? Yeah, over 50%. In fact, I even brought a chart. So it turns out, and this is really just a sneak preview, if there's only 58 of us in this room, the probability of 2 of us having the same birthday is hugely high, almost 100%, and that's going to cause a whole bunch of hurt for us on Wednesday. So with that said, let's adjourn here. We'll see you on Wednesday.